we live? Yes, excellent, good. Good afternoon. So what we can talk about for the next hour is thinking outside the synchronization quadrant, which means I have to say some meaningful things about what I mean by that terminology. This talk is placed in the C++ track. I would say that probably half the talk relates to C++. Specifically, the code that I'm going to show is C++. But the principles that I'm looking at are actually far more general. So it depends on what you're coming in for. There should be something here for you. Code, architecture. Architecture, good. Let's talk about architecture. So there are a number of different definitions floating around. The one that I generally find the most effective, the most useful, the most constructive is this one from Grady Booch. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change. Now, this is very helpful because it gets away from the false ideas of scale. What is the natural scale of software? Unlike building architecture, it's not as obvious. But there is a scale here, effort. How much effort is that to change? A very simple way of indicating and discovering whether or not something is architectural is whether if you make a suggestion of a change and somebody's face goes pale, and we can't do that. Or, no, we never do that. If people say you can't do it, then it's architectural, okay? And therefore, that means that it can relate to the smallest language feature as well as the more obvious major technology choices. Now, one such thing that shapes a system and is non-trivial to change is clearly something like concurrency, the presence of concurrency in any form. Now, one of the things I find interesting about concurrency and parallelism and our various definitions of all of these is the way that we have ended up accidentally being programmed to think in a particular way. You can almost play a word association game. In fact, this is what I did a few years ago. I did this with in 2 workshops. I did play this word association game, and I got the same results each time, which I found absolutely fascinating. First idea that comes into your head when I say concurrency, and as a room, everybody said threads. So in other words, what I found interesting is that was with the junior programmers, but in another company with a whole load of advanced developers who actually wanted to discuss higher level mechanisms. It was fascinating. If you catch people off guard, threads. Oh, damn! I didn't mean to say threads. I meant to say something like higher level and meaningful. It's still in there. It's still deep down there. Threads are the most powerful construct for introducing concurrency in any code base. And they are powerful like a goto is powerful. There was an interesting proof in the early 1970s that goto was the most powerful sequential construct. And what was meant by power is that you could build any other sequential construct out of it. And then you have to throw the Spider-Man quote at this point. With great power comes great responsibility. And it turns out we're not quite as responsible as we thought we were. The same goes for threads. You can build pretty much anything else out of threading constructs that expresses concurrency. The problem is they are too primitive. They are too raw. They are effectively the jump statement at this level. So we acknowledge that there are going to be threads, but that may not be where we want to write our code. We want to leave those further down. Now, the word association does not end there, because I threw another one at people. I said threads, and they all said locks or synchronization. In other words, that's kind of interesting. So hang on, why are you guys doing threading? Oh, we're doing threading because we want things to go faster. Why are you doing locking? Because we want them to go slower. Well, they didn't say that, but that's what they mean. Locks are the anti-thread. The purpose of a lock is to eliminate concurrency. So if your goal is to get some of this, then it's fairly clear whilst that may give you it, this taketh away. And this is a struggle that we often have. There's a lovely quote, and I just realized I've forgotten to put it in this talk, originally from David Butenhoff, who wrote the book on POSIX threads. And he said, you know what, we made a mistake calling them mutexes. We made a mistake adopting Edsger Dijkstra's terminology. We should have called them bottlenecks. Because then when developers talk to each other and have a conversation, they're more likely to think twice. Oh, you need to put a bottleneck in here. It doesn't sound quite so good, whereas mutex has this kind of like lovely whiff of computer science about it. Yeah, bottleneck, not so good. Okay, so what we realize is I'm going to pick on this quote from somebody actually talking about real building architecture. Architecture is the art of how to waste space, but I'm going to adapt it. Because when it comes to code, what we realize, it's about the ability and skill of wasting time. So let's talk about this thing, the synchronization quadrant. I found that I was trying to sort of classify things simply for a team. A few years ago, we ran a workshop on their development practices and some of the issues they were having. And I found that one of the simplest ways to clarify for them this, I put it up on a flip chart and then realized it actually was a really useful classification mechanism. Let's just break the quadrant diagrams. First of all, it's the afternoon, so your metabolism, your brain, and everything just gone into they've gone into a sleep state. So a quadrant diagram is your friend at this point. It divides the universe into 4, and there are 2 axes, and there are 2 things on each axis. It really doesn't get much simpler than that. And as with most quadrant diagrams, there's normally one quadrant that's either very, very good, or a quadrant that is very, very bad. Now, I'm going to break this one down to mutability. There is an axis of mutability. The data that you are dealing with is either mutable or it is immutable. And then there is the degree of sharing between threads. Your data is either unshared or shared. Now, you can subdivide this far, far further. You can say, oh, I've got a single writer and multiple readers. That's great, that's fine, but that's over in the shared quadrant. I'm going to keep this quadrant-like. And so here we have 4 places your code can be. I'm just going to make this really, really clear. Red, nature's color for bad, or in Far Eastern cultures and contractors, the color of celebration. Okay, this is the synchronization quadrant. Okay, you have mutable data and you have state that is shared between your threads. You will need some form of explicit synchronization in your code. Okay? I'm not saying you don't need synchronization anywhere else. It's just that the synchronization either belongs lower down at the lowest level, actually, in the processor, or it belongs in a library construct. So there may be synchronization. It's just that we don't want it all over your code. So, but there is this thing. But there's something about this quadrant. This is where most code ends up living. There are 4 possibilities, but like moths drawn to a flame, we are drawn, our code bases are drawn into this vortex in the top right-hand corner. And I have wondered about this for a while, and I realized having, I got a very, very, very long time ago, I got a master's degree in parallel computer systems. And so, you know, you kind of think everybody knows this stuff, and actually it turns out that they don't. But you've just happened to be been exposed to all this good knowledge. And it turns out as we tracked into the 90s and on, we ended up going into this quadrant over here. And I often wondered about this. And there's a simple cultural and historical reason. Before threads became commonplace, all our code was on the left-hand side, because by definition, you cannot share between threads if you only have one thread. So all the code was over here. And for historical reasons and our imperative background and resource constraints and so on, everything was in the top left-hand corner. A few things wandered down into the bottom left, but pretty much most code we're talking about is in the top left-hand corner. So when we added threading as a language construct, as a library construct, as a feature in the operating system, we ended up naturally moving straight over to the right with our code. And that led to the problem. If you look at books that are written in the 90s up until the early 2000s, whenever they introduce concurrency, they follow this idea. They're mostly about the locks. How do we lock stuff? And indeed, a lot of the literature published in the 70s and 80s was along these lines. It's about how do we lock. And all the constructs and proposed language mechanisms are all in that kind of view. In the last decade or so, we've kind of really shifted. It's not the game that we didn't know that perhaps avoiding all of this locking conversation was a good thing. It's just that it's become more normal and more accepted. So, yeah, we've ended up, unfortunately, with an awful lot of code over there. So let's talk about the qualities of such code. When you're dealing with code, there's a kind of simple right-hand rule that I quite like to use. The axes are not perfectly orthogonal, but then again, neither are my fingers. So it's a good enough approximation, but it allows you to reason about code reasonably simply. Functional behaviors, operational behaviors, and developmental qualities, okay? So in other words, the functional and operational qualities, functional as in the semantics, the operational as in resources, as in what many people refer to as the ilities that are not related to the development time. The development time stuff is your experience as a developer. Those other two refer to runtime qualities. And if we look at those, we can see that obviously when you are improving performance, you're moving along the operational axis. When you are refactoring, you are maintaining a constant functional axis, but you are trying to improve some developmental quality, and so on. It's kind of an easy way of kind of reasoning about your code. If you add functionality, you move along the functional axis, okay? If you fix a bug, you move along the functional axis as well. Yeah, you had a deficit of functionality, now you make up for it. So it's a nice, simple model, but I want to start, first of all, with the operational axis, this idea that the qualities of execution are one of the reasons that people are motivated to introduce some form of concurrency into their code. It turns out Shakespeare was on this one as well. I mentioned Hamlet this morning for memory management, but he's here talking about resources. The monstrosity in love, lady, that the will is infinite and the execution confined. The desire is boundless and the act a slave to limit. We're going to come back to limits again in a bit. The problem is you do not have the ability to run things at infinite speed. Everything has some kind of cost. No matter how brilliant you think your architecture is, it turns out this is the point at which our beautiful abstractions meet the laws of physics. And there are costs to the laws of physics. There's a rather good blog came across recently. Link is at the bottom. What are the costs of various operations from the kind of CPU perspective? And obviously this is going to vary from processor to processor, and so these are defined as ranges. Importantly, it's logarithmic. I rather like the display, the idea of light. How far does light go, travel during the time that this operation takes? Clearly he has a smaller laptop than me because it's not the diagonal on this one. This is 1 light nanosecond. I often use that as a measure when I'm telling people, so I was delighted to see he's done the same thing. That's 1 light nanosecond, which sounds, terribly fast until you realize that gives you a cycle time effectively. If that's the distance over that, that's a cycle time of 1 gigahertz, which is not so smart. It's really, you exhaust the possibilities of 1 gigahertz in a very short physical space. And then he goes through. These are orders of magnitude. The thing I want to draw your attention to, thread context switch. That's generally more expensive in terms of cost. The raw direct costs lie between a kernel call and a C++ exception throw and catch. Okay, stack unwinding the whole bit. But as he says in the article, this is quite difficult to measure because there are loads of indirect costs that go on. You can, and it turns out that those can be ridiculously expensive. This is one of those things that. And one of the great disappointments people have when they fire up threads hoping for linear improvements, what they suddenly discover is they're not getting them. There's a cost involved. There are lots of costs. Effectively, there are coordination costs. So if we take the idea to understand whether or not you want to introduce threading, if we take this idea, completion time for a single thread, and we're working on some task, the classic view of division of labor, we're going to throw n threads at this. Okay, that's brilliant. If everything's independent and everything is for free, and if you remember at school, you probably did some electronics at some point, and there was this rather brilliant assumption that was made when you're first introduced to electronics. What is the resistance of a wire that connects all your components together? 0. I know, isn't that brilliant? You're at school and you get superconducting wires. How cool is that? Yeah? But it's a beautiful idealization. So this is the way that people often think about threads. It's just like we end up with 0 cost. This is fantastic. Even without worrying about that, though, we haven't even looked at the nature of the task. We are assuming that everything is perfectly independent. It's not going to be. there is some portion that you can do in parallel. And tasks have interdependencies. If they need to talk to one another, share data, do whatever, then there will be some portion they cannot do in parallel. A lot of it depends on P. This is Amdahl's law. Now we're going to get rid of the ideal wires. Now it's quite difficult to do this in a simple equation, so I'm going to give you worst case and oversimplified view, but we get a shape out of it. Inter-thread connections, let's assume the worst case that everybody needs to talk to everybody else. That is the absolute worst case, okay? If you have that and you're a contractor, this is magnificent. You have a job for life, okay? But really, you don't want to be in this kind of mess. Let's assume that we've got some kind of concept of an average communication overhead. Average is a very difficult concept to apply in this case, but let's just say we've got some kind of typical communication overhead. And that's going to give you a curve like this. What that basically means is the minute you introduce threading the minute you divide many tasks across threads, you get a slowdown. It's not universal, but people are often surprised at how much benefit they do not get. This is the first thing you need to remember. It turns out that if you don't have the cost of a context switch, then just being able to do things really fast sequentially turns out to be an absolute winner. We see this classically in the sense that historically X-Windows servers sequential. They use basic reactor pattern and they just handle something, get on with it, handle it, get on with it. And they just do lots of tasks very, very quickly. And there is no need for concurrency. The minute you start hitting the concurrency barrier, you have to ramp it up quite a bit, and then you get something out of it. We're not even worrying about whatever else is going on in the processor. There's a whole load of other stuff going on. I'm just skimming and lurking at the surface here. If you want that, Sean's doing a talk later, and he will talk more about stuff like that, unless you've radically changed the slide since I last saw it. So I'm just scraping the surface here in terms of the bits that you can easily do and touch, okay, just with these constructs. So we have this, and there is this question of locality and cost. The landscape has changed as well. Every few years, we end up with a shift in our architectural defaults, the thing that developers think, oh, that's so obvious, you always do that, and it turns out it's not. So we're at this point. It's lovely. This is a blog from 2 years back. Adam Drake did this very simple task. Command line tools can be over 200 times faster than your Hadoop cluster. And he basically did this. He basically did this particular number crunching task. Not particularly big data, but for some people it would be big data. Obviously, what we consider to be big data is a function of time. Once upon a time, 1 megabyte was quite big data. So there is the point here that people have got into the habit of saying, right, distribute that. And you distribute that across multiple processors to the cloud with it. To the cloud with it. So he wrote this in Java, and then he wrote it again using Bourne shell and ran it on a single machine. Because it turns out the thing we now have. It used to be cheap processors across a network. It turns out that memory is way, way better. If you can keep it local, do so. You cannot beat the speed of light. It really is that simple. This is a key point. We've got an interpreted language here, but because it's able to use local memory, brilliant benefits. Now, speaking of that, time for some code. I'll do a very simple, I want to look at a couple of constructs and what is involved here, and I also want to place this on the synchronization quadrant. I'll do a very sort of simple, naive kind of map-reduce approach. We're going to map some operation called mapping across a number of tasks, and I've just realized I overdid that. That's the great thing about live stuff. You spot the bugs, and you can fix the bugs. You saw nothing. Okay, and that's good. There you go. Right. So we've got that. So then we end up with a whole load of choreography. Oops, all the sequencing has gone out of that one. Right, there we go. That's what I'm after. There's a whole load of noise that we get from C++ in its kind of classic form. I've got my data from begin to end. I've got a mapping operation, mapping. I've got a reduction operation that's going to combine everything with respect to an initial value. And then I'm going to code this up raw by hand. I'm going to create a vector of threads. I'm going to set up a loop where I go and launch a thread We don't even know that this is going to be appropriate. We haven't even looked at what cores are available, and I'm going to hit the threading really, really hard here, and fire off each task, and then I'm going to wait and join on them. And once I've got everything joined, at that point I can combine everything. I can use accumulate. Accumulate is the standard library default term for what everybody else calls reduce or fold. So we've got that. Okay. Now there's a few things we can do to tidy up here. One of which is C++ 14 allows me to just deduce the result type, and we're good with that. The C++ concepts technical specification allows me to get rid of all of that, which is marvelous. So that tidies it up a bit. Then if I take on board the parallel technical specification, I can now get a parallel version of for each that can vectorize. I can give it a policy. I can say, right, vectorize that. I've also got one for accumulate that I can now do a reduce. So reduce did get spelled correctly at some point. And we've got that. So if we look here and relate that, the bit that can although I'm doing the reduce, although I'm doing the reduction, I've said, well, let's assume that our operation will actually work. I'm missing an argument in there, I've just realized. Will actually work fine from one particular point of view. There is all the concurrency that we can really squeeze out of this is going to be in the for each bit. And the last bit is most likely better off done sequentially. So in that sense, that code is, from the point of view of the synchronization quadrant, the first part assumes that nothing is shared. Each piece of data is independent, therefore we're able to fire everything off in parallel. So there's no locking there. There is a synchronization point at the end, but that is hidden from us. And then again for the last point. But portion that can really be done in parallel, P is the first part. Okay, so there's another aspect here, functionality. People often throw threads at their code because they want to express functionality. Why does that make sense? Normally it's performance. Actually, we used threads for a very long time before we got multi-core. In fact, one of the first times that I was using threading was definitely well before the multi-core era. And our motivation was quite different. It was the expression of functionality. Where things are independent, I don't want to have to write my own scheduler to make them independent. I would like to be able to say, there's this going on and there's this other thing, and feel free to interleave them as and when. So not getting true parallelism, but some form of concurrency, the idea that I want decoupling between tasks. So from that point of view, we're saying threading not as a performance gain, but as a form of decoupling. These things are independent. Why should I have to make them dependent on one another by dividing up the task manually and creating effectively my own scheduler? So there are reasons for doing this. However, the expressiveness is the bit that gets us, and this is where lurking in the top right-hand quadrant causes us problems. A large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. John Carmack of ID Games. In a multi-threaded environment, the lack of understanding and resulting problems are greatly amplified, almost to the point of panic if you are paying attention. In other words, we struggle to reason about state in a code base. We struggle more when there's state to change. And then if we say, by the way, things can happen out of sequence and whilst your back is turned, then this is where the panic sets in. And if you do not have a healthy sense of panic, there is something wrong with you. You've not reached some Zen state. There is something wrong with you. If you are dealing at this level, it's just like, there's a lot changing and there are threads. You need to take a very rigorous approach to get away from that sense of panic. So, the most common example, best expressed here. Take me down to Concurrency City, where green pretty is grass, the girls, and are. It's things happen out of sequence. We have the problem of race conditions. This is why people often say, this is why I need locks. The problem is that we have this programmed into us to such a degree that people do not question why they have locks. And I had this conversation with a group. The conversation was interesting because I said, why do you have locks? And they said, because we have threads. And I said, yeah, but that's not a reason. Why do you have locks? And they're kind of looking at each other. And they said, well, yeah, because we've got threads. And I said, well, yeah, because otherwise it wouldn't be safe. Well, why would it not be safe? Why are you writing unsafe code? That's always a challenge. Why are you making your code unsafe? And they said, well, Yeah, because we're sharing data. And I said, yep, you still have not given me a reason why you're locking. And they're kind of looking at each other as if they were my teenage son. In other words, you're an idiot. Yeah. And then I said, okay, so why does sharing stuff between threads cause problems? And they said, well, because one thread might change something. And I said, well, hang on, wait a minute. That's really important. That's the most important thing you've said, and you left it till last. That should have been your opening sentence. We've got changeable state, and it's being shared between threads. Not we assume that all state is changeable. You should consider state change to be a privilege, not a right. But the problem is that the way we've been taught to program is the opposite way round. And so therefore we fall into this default way of thinking. So there are other surprises to be had when we start throwing locks at things. Locks mean ultimately you're going to end up with deadlocks. And there's a rather good summary of some Tannenbaum's points on the site that I found. Several ways to address the problem of deadlock. Just ignore it and hope it doesn't happen. This actually has a name. It's called the ostrich algorithm. Yeah, it's surprisingly popular and actually not as ineffective as you would think until you ramp up the number of states your system can be in and the speed at which it runs. Then it gets more exciting. And there are also a lot of systems a lot of threaded systems where these problems were started to happen with code that had threads and have been perfectly fine for years, but they've been single core. They'd managed to sidestep the actual issues. And there are some really subtle cases that can cause you these odd issues where, well, let's just restart the server again. We have to do it once a month. We're not entirely sure why. But there are the ones that happen in a far worse sense. We have to restart the server every minute. It's not viable. So this can work, but I'm not going to. I wouldn't put money on it. Detection and recovery. If it happens, take action. So people spend a lot of time coming up with very clever techniques for doing this. Dynamic avoidance by careful resource allocation, check to see if the resource is granted, and so on. So in other words, this is kind of an amplification of the previous point. But I prefer the fourth option. Prevention. Change the rules. Yeah, don't play that game. Sometimes people do this by imposing some kind of lock ordering or some form of lock discipline and basically saying this code, and so it becomes an architectural guideline. None of this code has any locks. This is the only code that can have locks. If you're going to plug this code into this code, here are the rules. If you follow these, all will be good. And it's a detectable thing. In other words, there should be no synchronization primitives, and you're only allowed to call this object. So these become a set of conventions and architectural guidelines rather than a sort of happenstance and accidents. So yes, we can do that, and we'll change the rules a little bit as we go. Now, I want to close this kind of consideration with this last aspect of developmental qualities. What are the developmental qualities when we start throwing things like threads at our code? When we start actually introducing these low-level constructs or even high-level constructs, what are we getting? Well, what would we want from our code? One of the things we want from our code is habitability. Habitability is not a common phrase that people throw around code, but I've been very keen on using it for the last few years. I first came across it in this book by Dick Gabriel, Patterns of Software, in the late 90s. And he makes this observation, a very simple observation we can apply to any code base in any language. Habitability is the characteristic of source code that enables programmers and so on, people coming to the code later in its life to understand its construction and intentions and to change it comfortably and confidently. It's a very simple idea. It's what we would define as habitability in a home environment or in a building. You want to arrive in a code base and basically say, yeah, I want this to be livable. This should be a comfortable place for me to work in. I shouldn't have to sit there and go, oh, please don't send me into that threaded nightmare. It should just be a case of like, right, okay, I understand what's going on. This is what we want in software. Developers can feel at home. They can place their hands on any item without having to think deeply about where it is. That's what we would like. But what we find in practice is a lot of threaded code is in exactly the opposite place. It is uninhabitable. It makes the rare vacuum of space seem like a nice place by comparison. So how are we going to get this? Well, there are a number of different qualities we want from such code. Testability is quite a nice one. Quite fond of that one. You'd like to know something about how it works. But there are a number of misunderstandings when we start talking about things like unit tests. Sometimes people have different takes on this. And there are different views. Now, one of the ones that I notice in a number of cases is where people say, well, we can't really afford the time to do unit tests. We don't find them particularly effective. Now, sometimes that's actually an indication of something deeper in your architecture. But I came across this paper a couple of years ago, beginning of last year, came across it, and then twice more later in the year. And it's a rather interesting analysis of certain distributed open source systems. Simple testing can prevent most critical failures, looking at actual production failures. But the statistic that leapt out at me is they actually revealed that something like 77% of the tests, 77% of the problems could actually be revealed with unit tests. So over 3/4 of the problems that they found could have been discovered with the unit tests. You didn't actually have to fire up the whole system in order to discover these. But that does lead to the profound philosophical question, when people say we want our code to be unit testable, what do they mean? And there's kind of an implied idea, which is quite difficult. People tend to think of their code like this. They tend to think of their unit tests. They think, when a unit test passes, it shows the code is correct. Actually, that's not what you get. And assuming the test is correct, okay, I'm going to give you that one. Okay, let's assume the test is correct. That doesn't show you the code is correct. When a unit test fails, it shows the code is incorrect. It's the other way. And this is rather important because sometimes people will. It gives you confidence, but that's not the same. That's not the same measure. And particularly where you start doing things concurrently, you cannot assume that green means it's good. It just means it's good so far. You can be sure that red is bad, but green is a rigidly defined area of doubt and uncertainty. In this case, you have to be very cautious with it. It's a level of confidence, but it's not absolute confidence. And the law of the excluded middle does not apply here. It's quite important to keep in mind. How do we achieve this? What helps us with testability? What helps us get away from that idea of like, well, I can't really test it because the architecture is so sophisticated? Well, actually it's not. It's probably a lack of isolation. Isolation allows the code to be testable, but there's something else. There's something far more important than that. Isolation allows you to reason about it. We are surprisingly good at reasoning about certain things, as long as they are isolated from others. But humans can be easily flooded with too much connection. When you have to take on board too much, you will not cope with everything. You will overlook something. So there's this idea, the more we are able to isolate things, the more we are able to reason about them in confidence. This is why people bang on about modularity and have been doing so for decades. It's not for mathematical elegance, it's actually the fact it respects being human. Other qualities that may help us. Immutability is one of those things that helps us. Things being in sequence. It turns out we're really good with this happens, then that happens, then the other happens. But that is, at one level, it feels like it's at odds with our desire for concurrency. But we are good at reasoning sequentially. And one of the ways that we can reason about this and kind of have the best of both worlds is by the introduction of asynchrony. But obviously not everything that is asynchronous is easy to comprehend. That's my favorite one recently. 10 things you'll find shocking about asynchronous operations. Beautiful. Just one of the best I've come across in terms of it captures it rather elegantly. So there is this question. If I take operations that are synchronous and I would like to make them asynchronous, what do I have to be aware of? Well, obviously there's a question of ordering. How do I pick up results? We talk about futures in POSIT 4. Immediately return a virtual data object, a virtual proxy, effectively, called a future, also known as an IOU, to the client when it invokes a service. This future only provides a value to clients when the computation is complete. Now, you can take future-based computation a very, very long way. I propose not to, because I also know that Sean will be talking about that way, way more deeply than I'm going to. But I'm going to introduce the basic concept here. If we do this sequentially, we get a result from a function. Now, if we want to do something after it that is independent, then we've just forced this into an unnatural sequence. There's a thing I want to do, call a function. There's another thing that I want to do, and then I probably want to combine these things later. I could switch them around, but same issue. So what we do is we separate this stuff out, and we say, okay, let's launch the function asynchronously. I'll pick it up as an IOU. I'll go and do other stuff. And when I actually need the result, then I'll go and get it. This is the kind of basis of where we can start taking certain data flow ideas. I will interject at this point, though. I think the C++11 syntax for this sucks completely. I had a model that I published a number of years ago, actually made it into proposal form, where I decided that, I said basically everything should be a function, and we should follow a function model. And the idea is that a future is effectively a thread, or is effectively a function object. Thread is a verb. You take a function and you thread it. It is not a thing. It is a verb that you do to something. What you get back is something that allows you to join it and pick up the result, and everything is done as a function. You thread things using functions. The result of calling one of those is itself a function. If you want the value, then that is itself a function. So you can use that wherever function objects are expected. You can extend this model quite a lot. It's quite a regular one and fits with the C++ style. This whole get thing doesn't really appeal to me. However, that's a by the by. But there's a kind of an idea there that these ideas, that these practices have been around for a very long time, and people have got different ways of expressing them, and different languages have different ways of expressing them. But if we go beyond the future, which sounds very dramatic, if we go beyond the future, I want to pick up on this general observation from Russell Winder. Instead of using threads and shared memory as our programming model, we can use processes and message passing. Process here just means a protected independent state with executing code, not necessarily an OS process. Now, we have a lot of terminology collision. We sometimes refer to such systems as message passing, but it turns out we've ended up with lots of terminology for the same constructs and subtle shades and variations between them, which I'd like to explore. But Russell points to two things. Languages such as Erlang and Occam before it, Erlang uses the actor model and Occam uses something called CSP, have shown that processes are a very successful mechanism for programming concurrent and parallel systems. And such systems do not have all the synchronization stresses that shared memory multi-threaded systems have. And more importantly, they do not have the reasoning challenges that such systems have. In other words, the code is very localized. It feels very sequential. It has this idea, and this is an idea that I guess I've been pushing for a while by various names. It allows you to think in a sequential bubble. I said that sequential reasoning is something we're quite good at. What you want from your code is that each part of the code is sequential and has no idea about the world of concurrency, the construct of threads, or anything like that. In essence, it becomes the idea that any piece of code you write is therefore more easily testable because it itself is sequential and simply reasoned. The idea is that you then, through a compositional approach, whether it be wiring, whether it be coordination language or something else, you then say, and here is where we introduce the concurrency. We take our rather simple modules and wire them together. But there is this idea that wherever you are, the world should look sequential. And if you're getting data, then that data arrives as if it were events, or it arrives because you pull it from a channel of some kind. But you don't have the idea of, I am interacting with another thread. You try and avoid that kind of structure. In one sense, this is what can be called a virtual uniprocessor. For a number of decades, computer science spent a lot of time talking about virtual multiprocessing, how to give the illusion of parallelism on a single core, whereas virtual uniprocessor is you've got massively parallel hardware and you like to give the illusion of sequential reasoning. And that term was first applied, to the best of my knowledge, to describe the human brain. We have this beautiful illusion of a stream of consciousness on this ridiculously parallel hardware, and it turns out that's not a bad way of thinking about stuff. So you want your code to have that kind of feel to it, and these models generally give that kind of feel. So the most fundamental construct. Let's talk about queues for a moment. Queue, you got producers. You've got a producer there. You've got a consumer there. You've got a queue in the middle. So the producer and the consumer represent activities that are decoupled from one another with respect to time. The most obvious concept of time in this case I'm talking about is threading, but decoupling through time is what we're talking about. I can actually have a perfectly sequential system where I have a producer producing into a queue, followed by a piece of code in the same thread that unpacks that queue as the consumer. So the idea is when we say decoupling through time, that can mean true parallelism, but it can actually mean we've ordered things sequentially, or we're doing things by a time trigger or whatever. The idea is that we're trying to create a model that almost doesn't care at some level. So this is a simple one-to-one relationship. This guy's doing something, maybe he's doing I/O, this guy's doing something else. Yeah, fine. Now, that's the simplest arrangement that you can find, and we're going to come back to it later. What you may find is that you're taking things from lots of different sources. There are lots of different places you can be getting your input from, or alternatively, these guys are running at different speeds, and therefore you would like to pace them. So you've got an n-to-1 arrangement here, or it may be the other way round. And there may be a logical thing. Maybe you've actually got ports out here, and so on, that you want to send things through. So there's reasons either physical. Physical or physical. Physical in the sense of communications, or physical in the sense of time. So you can decouple them like that. Now, that's an n-to-1 and a 1-to-n arrangement. You may also find, but I would generally recommend that the n not be the same on both sides. M-to-n, you may find that it makes sense to serialize things. There may be a lot of stuff coming in on the left-hand side. Again, I/O rather than computational tasks probably makes more sense for this arrangement. And on the right-hand side, you want some kind of fan out to different tasks. And other configurations. Use more than one queue. Okay? And likewise on the other side. And then, obviously, I guess the degenerate case is where you realize actually you've just got a one-to-one arrangement, just lots of it. Okay, so you can keep combining these and crossing over. You can have one thing posting to lots of queues and lots of things picking up on the other side. There's lots of arrangements. I could just keep copying and pasting this slide to generate all of them. But the idea here is the queue is the most general construct at this point for decoupling in time, and it is the performance and characteristics of your system that will dictate which configuration you're interested in. Now, from a code perspective, let's try and wire some of this together and get a feel for what this might look like. If we create a queue of anything, so make it generic, so we've got a template there, I'm going to start with the simplest idea, is that I can send something, and I've got a choice of receiving it. I'm going to do this as a non-blocking receive, a try receive. I can pick up a value. If there's nothing there to receive, then I will return false. And if somebody's trying to, if I assume that I've got a very simple locking mechanism, well, let's do it sequentially first. If there's nothing there, then I'll get back false. I'm just going to use the standard library deck type. So that's going to be nice and easy from that point of view. If you send, you're just pushing back. And if you try, well, if you try and receive, if there's something there, we do something with it. Otherwise, we don't. It's as simple as that. We return false. So that all works rather nicely and is profoundly not sequential. Or rather, profoundly not concurrent in any way, shape, or form, not safe. So we reach for our bottleneck, throw in a mutex, and we say, OK, now we can start sharing this between an arbitrary number of senders and receivers. And that allows us that. And this works quite nicely for the non-blocking approach. And this may be sufficient. This may be what you want. And so we use a scope lock to ensure that we have a critical section that's automatically locked and also exception safe. And we kind of do the same on the other side. But now we've got two reasons why we may fail to return a value. Previously, it was if I try and receive and there's nothing there, I return false. Here, there's now another reason. I tried to receive and either there was nothing there or something was being put in at the other end. Now, if you know more about the characteristics of your system, then you can start separating locks for your ends, but I'm writing the most generic form of queue here. I cannot assume that the ends are always going to be far apart. I cannot make certain assumptions in this case, but I'm giving you something that works reasonably well. So that's the basic construct. Now, the next thing we might want to put in is a receive. That is a blocking receive. Sometimes we don't actually want to do anything else. There is nothing more for this thread to do. I don't want to just sort of say, I tried to receive and I failed. What do I do now? I'm going to spin lock. No, that's probably not a good idea. Perhaps this task exists only to work with values. So there are further layers we can put on this, but I'm going to leave this at a fairly raw queue level, but we're still hiding the lock. And I want to be able to block on that receive until I get something. Now, we could go further. So I'm going to throw in a condition variable there. We could go further and also have a try receive. Now, I'm going to make a point here. I'm not going to explore it much further than this. Because I did mention the Shakespeare quote. Everything is a slave to the limit. You don't really want a queue like this in production code for the simple reason that there's no bound on the queue. if something goes wrong, if something goes wrong, you've not anticipated it, you can use up all of memory, which is really not what you want. This queue can fill up to infinity, or the amount of memory you have available, whichever comes sooner. And I think I have a pretty good idea which one's going to come sooner. The idea is you can end up with, if you end up with a locked receiver and you're still sending, that queue is just going to pile up. That's why people care about queue lengths in production code. So really, you actually need to have the idea of a bounded queue. These are great for prototyping things, and they will work fine in certain classes of system. But either you have to have a hidden constant, or you need to be able to parameterize it yourself and say, no, there is a maximum size for this. We are not going to let this grow until all of our resources have been exhausted. And you can choose to embed that within the queue construct or put it somewhere else in the code, but it has to exist somewhere. Do not assume that they should be unbounded in production code. However, to keep things simple, I'm just going to say, right, let's not worry about that. I've talked about the bit that sort of, there's a heads up there. But the next thing is, there's some code here. I'm not really going to worry about that. It just does the right thing. We've got a condition variable. We will continue blocking or suspending while there is no content to receive. And when there finally is, we'll actually do something and actually pop the result. Now, there's a few other bits and pieces that we can start adding in to refine the code. I'm not going to worry about those. I want to go back to the idea that we've got a basic functioning queue. I want to go back to an idea that earlier on I mentioned we'd be coming back to the one-to-one case. There is a particular name. The idea of queue is that we can have a queue allows many-to-many, one-to-one, one-to-many, many-to-one. A channel is a special case. A channel is, and we borrow the terminology from CSP, communicating sequential processes, is a single point-to-point of contact. Go also uses the term channel, but is perhaps not as strict. It really just means queue at one level. But it borrows some of these ideas. But strictly speaking, if we have a channel, there is one sender, one receiver. It is a dedicated line of communication. It is a dedicated queue, which allows certain simple optimizations. I can have a channel. I can just basically say that queue that I just showed you, I'm going to go with that. Or alternatively, I can create something else that's a channel and have some rather clever low-lock implementation that takes advantage of our known limits and the fact that there's only one sender and one receiver. We can start taking advantage of this knowledge. Whichever one we do, I'm just saying that the configuration I'm interested in here is this one, that there is this dedicated receiver. So we're going to take one of those great problems of software development that taxes everybody's minds and imaginations, FizzBuzz. It is not exactly the hardest problem in the world. And I'm not going to look at clever ways of parallelizing it. I just needed something for the code to do. So here is the thing for it to do. If a number is divisible by 3 and 5, you get FizzBuzz. By 3, fizz. By 5 buzz, otherwise you just get a stringified form of the number. That's it. There's nothing interesting, parallel, or whatever about this. That's not what I want. I just wanted something to chew on. The parallel bit comes in here. What we're going to do is we're going to set up a FizzBuzz server, because that's what everybody needs. It's called FizzBuzzer. Okay, and what it's going to do is it's going to take an input channel, it's going to have an output channel. On the input channel, we're going to receive integers. On the output channel, we're going to send strings. Nice and simple. So now, from this point of view, if we look at this piece of code, there's absolutely nothing sequential, or there's nothing parallel, or nothing concurrent, rather, about this piece of code. It is I'm just basically taking in a channel and another channel, and I'm going to use both of those. I'm going to just run around and do stuff. That's fine. This is actually quite easy to test. I'm going to set up main. We're going to have a channel out and a channel back. We're going to launch that as a separate thread. I don't have to. There's absolutely nothing here that's of interest here. But I'm going to go and send something, and then I'm going to get back a result, and I'm going to print it out. Really, nothing exciting going on here. I can resequence. I can mess about with the syntax a little bit and make it feel a little more C++-y. But what's more interesting here is I'm able to decouple and have a thread that's out there waiting for stuff, send it a whole load of requests, and now the channel, the return channel, the back channel is now full, and then I pick up the results separately. So now we've actually introduced some slightly more meaningful concurrency. Not particularly meaningful, but the idea here is I'm able to rearrange the code from that point of view. The channel concept, a specific out and back approach, is a really simple way of decoupling pieces of code. It allows me to actually fill up stuff, prime something for testing. So some people might say, oh, I'm mocking it. Well, I'm not mocking it at all. I'm just simply giving it a preloaded queue. I can get rid of and rearrange this relatively easily. It's a matter of wiring. It doesn't mean you can't get deadlock. Yes, you can. But it means that it's now down to the wiring rather than the core logic that's going to give you that. And is there anything else to say about that? No, that's all the FizzBuzz is going to do in renewed syntax. So let's look at a particular application. And again, the terminology, pipes and filters is really built on channels, but we talk about it slightly differently. Again, a pipe is the idea of a dedicated point-to-point piece of communication. Very powerful from a general point of view in terms of thinking about composition. We divide an application's task into several self-contained data processing steps, connect these steps to a data processing pipeline via intermediate data buffers. We see the pipes and filters model allows us the introduction of concurrency, but it also allows us expressiveness. We find that many people, and you can see it in the Java streams model, without introducing concurrency, it's a very profound and useful way of reasoning about a task, because it is based on a functional programming model. A lot of people don't realize this, but this rather good point was made by John Purdy a couple of years back. Concatenative programming is the style. It relies on function composition rather than function application. And this is the basic reason Unix pipes are so powerful. They form a rudimentary string-based concatenative programming language. So this is a very simple idea. Each step, it's a compositional step. You're going to take data, you're going to process it. You're not going to worry about, you're not going to introduce side effects on the data because you pass on new data to something else. And it is a particularly different style of functional programming that is not the same as the classic applicative approach. And there's a lot of benefits to that without concurrency, but we're going to throw some concurrency at it. So I'm going to pick on sort of a very simple idea. What we've got here is we have some kind of source, and the arrangement is that we have a filter, then we maybe have another filter, and then we have a sink, and they're connected together using these pipes. I'm going to pick a not particularly meaningful problem, although this is one of those ones that came out of a rather interesting conversation about Friday the 13th. We had a Friday the 13th last week, so this seems timely. If you are superstitious, then we should have a proper conversation, but that's nothing to do with C++. If you are superstitious and you fear Friday the 13th, then you might sit down and write some code to decide when the next Friday the 13th is. You might do this in a kind of raw C approach. We're going to move this to C++, and not a lot of change, actually. The C++ chrono library, actually, if I were to port this to that, I would end up using more keystrokes, so I'm not going to do that. I'm going to just leave us with the raw stuff. This will find you the next Friday the 13th after the one that you the date that you provide. So this is all good. Now, so what we're going to do is we're going to break this one down. Instead of expressing the logic this way, I want to get a steady stream of Friday the 13th. And what I'm going to do is I'm going to turn this into a pipes and filters arrangement. And I'm going to start off like this. I'm going to say, right, first of all, we need to generate all the days of interest. You give me a date, and then we will just generate. We will loop forever. Then what I'm going to do is I'm going to filter in. I'm going to select in the 13th of every month. Okay, so this is how we do. This is a simple way of doing AND with pipes and filters. Okay, what I'm going to do is I'm going to select in every 13th of the month, and then I'm going to select in all the Fridays. And what I get out is a steady stream of Friday the 13th, which I will then display. So I've broken it down into a pipeline. And so we're going to wire this up. We're going to have a channel for all the days, and we're going to arrange this so that the days are from the start. Yeah, unfortunately, the outlining here has got bleached out by the projector. We'll have days from the start, and we'll wire it into days, and that's just going to go on forever. Actually, they don't go on forever. They tend to they will hit a limit. It turns out, disappointingly, we're not allowed to compute to infinity on this. But you know, what we're going to do is just keep on looping, generating days. We'll move forward a day at a time. Then we'll wire up the next bit by saying, okay, you give me all of those days, that's the input, and then I'm going to give you the output, which is only the 13ths. So I'm going to just select in, read a day. If it's the 13th, then I write it out, otherwise I'm not going to. Then the next one, I only want the Fridays, and we wire that one together, and then finally we actually display it and we pick that stuff up. So there's a nice little pipeline progression there. That will give us all the Friday the 13th of interest. And there is a simple idea here. We can rearrange. There's a few things that we can rearrange. We can actually, I've done this in a more classically CSP style, in the sense that what I've done is I've created functions that take channels. It is possible to invert this relationship and say, here's a channel and I'm going to associate behaviors with its ends. Which is a sort of an inversion of the model that I've got here. But I'm going to leave that one to one side. There's quite a lot that you can do with this once you start down this road. So there's a sort of an elegant side to that. If your architecture fits that, that's great. Very easy to reuse, far easier to compose and work with than other pieces of code. But there are most interactions that we want to probably introduce threading into don't really fit a pipeline model, a one-way data flow. We might need some interaction. And at this point, this thing that I did many years ago for my master's thesis was actor-based systems. And one of the things I worked with was a language called ABCL, actor-based concurrent language, or an object-based concurrent language, depending on which version you read. And when we talk about raw multithreading, Andrei Alexandrescu's quote is one of my favorite ones. Multithreading is just one damn thing after, before, or simultaneous with another. But what is actor-based computation? Actor-based concurrency is just one damn message after another. You are in this sequential bubble. Everything is sequential. You just receive something, you handle it, you pass it on. But that's obviously, it doesn't have a unique claim to that. So let's have a look at one of the classic approaches, which is monitor objects. A monitor object is the way that Java decided to bake into the language. Every object is effectively a monitor object, which means that it can be, it has a lock over the whole object, and it can be synchronized. Every method can be synchronized, or part of the method can be synchronized in execution, and there is a locking scope. It's the idea of passive data objects that have such synchronization built in. So that's great, because that shouldn't be our code, it should be somebody else's code, but and it is very lock-based, and it doesn't work well in a compositional sense, but it can be okay to write. And if we imagine something like a phone book, on which we're going to provide basic operations, an update operation for somebody's name and number, a drop operation to drop an entry, and a find operation that optionally returns a string if nothing's there. So optional, it is now 2017. Optional is now finally in the C++, or will be in C++ 17. So that saves all those null things, or using empty string as a marker. So basically, if we find the name and it's there, we get a result. If we don't, then we're told that we don't have a result. And this is in optional appears in other languages, sometimes called different things, fallible, maybe, and so on. So got that structure. We're going to have a simple mutex model like we had earlier on. And we can go ahead and we can build this stuff up. We can update. It's an upsert operation. We can drop. And then we've got the find operation. So in action, what we're going to end up with is something like this. We create a directory. We have our phone book. In another thread, we go and look for Thomas Anderson. Thomas Anderson is not yet in the phone book. So we've got an updating thread. So we've got two threads of interest here. The directory thread is actually passive. We're going to go and update that. Next time we try and find Thomas Anderson in another thread, both of these operations will be ordered in some way and mutually exclusive, so therefore we are guaranteed of some kind of coherence, and we will get some value. If we go and look for Neo, Neo's not in there. We're going to update with Trinity, we're going to update with Morpheus, we're going to update with, we're going to drop Thomas Anderson, we're going to add Neo. Now when we go and find Thomas Anderson, will not be found, but Neo will be. and because he is the one. So we've got a simple model there. So monitor objects are very attractive and very simple at that level. There is another approach, which for reasons of time, active objects we could go into, but I'm going to leave that out for your comfort. But I wanted to put them in there. Why am I showing you something and then saying I'm not going to show you it? I'm putting that in there because a lot of people confuse active objects and actors. They are not the same programming model. They are potentially related, but they are not the same programming model. The actor model has a different outlook. The actor model, I'm not going to show you a full actor model. I'm just going to build it out of the, build a very, very, very basic version out of the queue construct and the standard library thread we had earlier. Also, in C++ 17 will be standard any, a variant type. There are actually two variant types. This is a universal variant type. And what I'm going to do here is that phone book, you'll notice I've changed it into a function. It is, what we're going to do here is we're going to bind it together. We're going to say, look, here is your queue. You have an associated queue. And anybody can talk to you using this queue. We can be more specific about the message set, but I'm going to leave it as open and generic. Message set here, I'm going to say, well, you can have an entry. Either you're giving an entry or you're receiving an entry. In other words, it's a name and a number. You can have a no entry. Either you're telling the phone book, please, I don't want this anymore, or you're returning this entry does not exist. And you can have a find request. Here is a name, and here is the return address. Please send it back on this queue. Okay, so there's the idea that somebody can talk to a running function. That is the basis of the actor model. It's not that we are creating a classic object and putting locks in it. It is that we're creating a function and we are now communicating with a running function. This function, it doesn't reveal its own state. Its private state really is private. It's local variables. In fact, let's actually have a look at that. Here is the phone book. Here's the scope. It's going to get a bit messier. You can tidy this up, but I realize that for reasons of time, well, that's really what this whole talk is about, isn't it? Time and temporal decoupling. But for reasons of time, I'm not going to go into the details of it. So I'm going to do the kind of the raw, ugly, almost assembler-like version, but show you the basic construct. Here is the private state. This was previously private, actually private within an object, but this is now just a local variable. The function is just going to keep on requesting. I'm not going to put any termination in it. It's just going to loop forever, or Control-C. And the only operations that it can do is to affect entries. There's no kind of clever thing that somebody can do to get their hands on your private state. And that is the private state entries. So now we're just going to repeatedly handle requests. We pick up a request. Now comes the ugly bit, is I now have to go and do a bit of type dispatch. This is the bit that you can tidy up with a little bit of jiggery pokery. But what we're going to do here is we're going to pick up, is it an update? Have I received an entry? If it's an update, then I update. I update the entries with update name and update number. On the other hand, is it a drop request? Am I being told no entry? If it's a drop request, then I will erase that entry if that's the case. But the bit that's interesting is, notice neither of these requires interaction. When another thread, another actor, is basically communicating with you and saying, I'd like to add this entry or please drop this entry, they're not expecting a response. It's asynchrony without any kind of blocking return. There's no futures involved. They're doing this. But now we need to talk to somebody. And that's where the find is quite a good example. Somebody's going to send us a find request. Please find us Neo or Thomas Anderson or whatever. If the entry is not there, we need to tell somebody it was not there. If the entry is there, we need to tell somebody, we need to talk back. In this case, the return address is useful. An important thing that is often overlooked in actors is you don't have to actually return the call to the caller. You don't have to return the result to the caller. What they can do is they can set this up, and this is perfect decoupling. I'm going to make a request of you. You talk to that guy over there. Okay? It's not an actual return address. It's really a forwarding address. And it may come back to the requester, but it may go on to somebody else. So what we're going to do here is we've got this. If it's not there, we're going to use the queue that was given to us and say, look, there was no entry. On the other hand, if it is there, there was an entry. So what we've got here is a proper message handling loop, but all baked into constructs that are now available in the C++ library, plus the queue construct that I added in earlier. In execution, that's going to the call. We're going to move away from the idea that we're dealing with functions. We're going to do something that's a little more message-like. So I'm going to set up a directory. Then I'm going to launch a thread that holds the phone book with the directory, and then I'm going to say, right, okay, I've got a queue, and I would like to find Thomas Anderson. Please return it here. We're not going to find anything, so I'm actually going to pick that result up. What I should get back is no entry Thomas Anderson. In another thread, we're going to have an updating thread. So we've actually got 3 threads running here. We're going to have something updates with Thomas Anderson 1. Back in the requesting thread, we're able to now find it. We pick up a result, and that should be the result that we get. We can go through, add Trinity, Morpheus, drop Thomas Anderson, and add Neo, because he's the one, and we can now find Neo, and we get that back. What we've done there is that is the raw ingredients, if you like. This is the actor model broken down to its most fundamental level. And clearly, with a little bit of imagination, and if you've got experience of actor models in other languages, you can immediately see the opportunities for wrapping that up. But just based on a queue and a thread, we can actually affect this model and note where it goes and what style it gives us, that our messages become first-class objects rather than methods, and we get this inversion that the function itself becomes a running object that we communicate with. Okay, so sort of bring that to a close. There's an awful lot in there, and it's definitely time for a coffee. But I'm going to go back to John Carmack. He said, you know, it's a point there is that what we've ended up with is a number of things that are actually relatively functional in their nature. Functional style makes the state presented to your code explicit, which makes it easier to reason about, and in a completely pure system makes thread race conditions impossible. The idea is that we are explicitly not thinking about, I have data that I wish to share. We are thinking about, there are things to be done, who do I talk to? That kind of approach isolates. It's a slightly different philosophy, but using the same basic language, you end up with a very, very different architecture, and one that is more composable. So hopefully, the one thing we've learned about thinking outside the synchronization quadrant is that our default desire to put locks around everything when we care about speed is going to be thwarted because the thing you always have to keep in mind is all computers wait at the same speed. And this is the problem that we've been encountering as people have been trying to scale things up. What they've learnt is a number of lessons, sometimes the hard way, and particularly now that we are moving from, at the moment, I would sense that we're moving a little bit back from operating system processes to threads, because we've discovered we have a remarkable amount of memory available. This is worth keeping in mind, and not to say, oh, now I'm in the same process, I can just go back to my old C-like ways of sharing everything and just adding locks. No, the lessons that were learnt, pushing things out where you genuinely couldn't share them, those are valuable and worth keeping in mind. I hope that's been useful. I'm around for any questions as I'm unpacking. Please feel free to ask. Thank you.